e to the, yes, a square over 2 sigma square 2 pi sigma e to the a square over 2 sigma square over 2 pi sigma, and the integral from minus infinity to infinity of this guy. Okay, so imagine that exponential of this guy. Exponential of this guy. Okay, let's call of this, it's exponential of this guy. And integral with respect to what you call dy. Now here is an interesting thing. In this expression, so in the bracket you have these two parts. In this expression there is no y actually. So the exponential of this plus this can be written as exponential of this multiplied by the exponential of this actually. And I can take that exponential outside of integral because it does not depend on y actually. So hence, what you're going to get is e to the a square over 2 sigma square by 2 pi sigma, okay, and plus, so this, since this is the power of exponential and you already have an exponential here, so these both would be added, so you're going to get a square over 2 sigma square 1 plus sigma square, okay, this is what that you're going to get, times the exponential of e to the minus c y plus a over 1 plus sigma square, okay, chi square and dy. So this is what that you're going to get actually. This is what that you're going to get. Now, in order to turn this into, as I said, this form, e to the minus t square by 2 dt from minus infinity to infinity, I need to make a substitution. Okay. And what would be that substitution? That substitution is going to be that let's assume that your what? So let's assume that your x is maybe x or whatever is equal to this square root of c, that is square root of c. Yeah, I mean, if you wish you can do it. Square root of c y plus a over 1 plus sigma square actually. Let's assume this. Okay. Let's assume this. Let's assume this. And let's make this substitution actually. So when you're gonna make this substitution, what you're gonna get? Your dx in the terms of dy, your dx in the terms of dy will become square root of c dy. Okay? This is going to be square root of c dy. And when you substitute the limits, so as y goes to minus infinity, surely x goes to minus infinity, and as y goes to plus infinity, x goes to plus infinity. Okay, so there is no doubt about it. And now you do what? You convert everything in the terms of this actually. So you're going to have, by the way, if you simplify this, so you're going to get a square times 1 plus sigma square plus a square over 2 sigma square 1 plus sigma square. So it's going to be a square times 1 plus sigma square plus a square. So it's going to be a square plus 1 times sigma square plus 1. So it's going to be a square over 2 sigma square if you simplify, because okay, so it's going to be a square over so you're going to get a square plus 1 over it's going to be a square plus 1 times 1 plus sigma square over what? Over yes, over 2 sigma square 1 plus sigma square. Okay, so I hope that I have correctly calculated the LCM actually. So 1 plus sigma square, a square plus a square times 1 plus sigma square, a square plus 1. Yes, you can get this actually, and hence you can get rid of this as well. What will be inside the integral? So inside the integral, this is going to be e to the minus c, e to the minus x square actually, e to the minus x square, okay. E to the minus x square, and dx will become the square root of c dy. Okay, square root of c dy. By the way, in order to make even this more interesting, I can make an assumption that square root of 2 x over square root of 2, yani x square over square root of 2 is going to be equal to this, okay? So I can make this substitution, x over square root of 2 square root of c times y, y plus a over 1 plus sigma square. So you can have this, and once you have this, you're gonna have a 2 here. So the good thing with this is going to be, this will become e to the minus x square by 2, and here you're going to have a square root of 2c. So I hope I'm making correct calculations. I'm going to have 2 pi sigma. So we have 2 pi sigma here. So you have e to the a square plus 1 over 2 sigma square. Okay, this is what that you're going to get, divided by square root of 2 pi sigma, while this will become what? So you take square root of 2c out, and the integral of the square of this is equal to, what do you call, square root of 2 pi. So what is going to remain inside the integral of it is really square root of 2 pi. Okay, this is what that you're going to get actually. So finally, the integral that you want is going to be am I doing a mistake actually? Yes, I am doing a mistake. That mistake is that this a square minus 2 square sigma should be negative actually. So it should be negative. And if it is negative, what would be the outcome then? Okay, so just a little bit of modification. So you have a square over 2 sigma square 1 plus sigma square minus a square over 2 sigma square. So if you simplify it, you're going to get 2 sigma square 1 plus sigma square and 2 so it's going to be a square, okay, minus a square minus a square 1 plus sigma square. Okay, so you're going to get 1 minus 1 plus sigma square over r. Okay, so it should be other way around actually. It should be other way around. So this will become what if you pull out a square. So you're going to have 1 minus what do you call sigma square. So this will ultimately will be equal to minus a square over 2 a square over 2 1 plus sigma square. This is what precisely that we wanted actually. 1 plus sigma square. If you simplify this expression, this is what that you're going to get actually. So you will not have this, but finally what you're going to get is minus a square over 2 times of 1 plus sigma square. I was thinking where is the minus actually, because minus is crucial. And you're going to have minus a square over 2 times of what do you call 1 plus sigma square. Okay. And what will happen actually now? So if I get rid of this, what did you get finally? So you're going to have square root of 2 pi will get rid of the square root of 2 pi. So what you can do is that, okay, if you keep this as some constant that does not depend on a, so this is a constant that does not depend on a, it only depends on sigma actually. Okay, and if you wish you can make more simplification, but what remains is going to be the exponential of a square over 2 times of 1 plus sigma square, okay, and divided by square root of 2 pi sigma. This is what that you're going to get at. Square root of 2 pi, what do you call sigma? And what overall calculations we were doing. So the overall calculations that we were doing is that we were trying to calculate fx or x plus y of a actually. And what does this show? This shows, okay, so if we be a little bit more precise and try to calculate, for example, this 2c, square root of 2c by sigma, then c is 1 plus sigma square, okay? C is 1 plus sigma square over 2 sigma square. So this is going to become what? This is going to become what? This is going to become, by the way, I mean, if you, okay, so we can make these calculation precise. Okay, just substitute the value of c and see what final expression that you get. But what you get is going to be some constant that does not depend on a times the exponential of this actually. Now if you carefully look at this, what is this? This is the PDF of the normally distributed random variable with mean 0 and variance 1 plus sigma square. This is roughly the PDF of normally distributed random variable with mean 0 and 1 plus sigma square. So this means, hence you can say the conclusion is what? Okay, so after a lot of these messy calculation, not difficult calculation basically, it's a straightforward superfluous calculations. You can do them for yourself, okay, for more details. So the conclusion that you get is that we prove that if x is normally distributed with mean 0 and variance sigma squared, and y is normally distributed with mean 0 and 1, then x plus y would be normally distributed with mean 0 and variance 1 plus sigma squared. Actually, this would be what do you call the conclusion. Okay? And now let's move to the claim. Okay, the key claim that we had actually. Because what I want to show now, that using this fact, I can prove my claim actually. So that's for the sake of simplicity, to distinguish the random variables. Let's not use again x and y. Let's use some other random variables here. Let's x1 is a normally distributed random variable with say mu1 and sigma 1 square. Okay, and x2 is normally distributed random variable with mean mu2 and sigma, what do you call, 2 square. The claim is x1 plus x2 would be normally distributed with mean mu1 plus mu2 and variance sigma 1 square plus sigma 2 square. This is what the claim that we will like to show using this fact. And how to show it is this case. How to show it is this case. There's a way to do it. Let's write x1 plus x2 in a different form. So let's write, can I write x1 plus x2, this expression x1 plus x2 in this form, which is sigma 2 times x1 minus mu1 over sigma 2 plus x2 minus mu2 over what do you call sigma 2 plus mu1 plus mu2. mu1 plus mu2. Okay. Now I'm going to make use of this fact. Let's call this x1 minus mu1 over sigma 2 the random variable x, and let's call this y this x2 minus mu2 over sigma 2. By the way, you can see that sigma 2 will cancel out, mu1 and mu2 will cancel out, and you will recover x1 plus x2. Okay. The question, what is the distribution of x actually? So if you compute, for example, the average of x, mu x, or the expectation of x, the expectation of x is going to be expectation of x1 minus mu1 divided by sigma 2, so it's going to be 0. What would be expectation, the variance of x1, the variance of x? So the variance of x is going to be the variance of this guy, so it's going to be 1 over sigma 2 square times variance of x1 minus mu1, so the variance of mu1 would be 0, so it's going to be equal to variance of x1, and it's going to be equal to what do you call sigma 1 square actually, and hence the variance of x is going to be sigma 1 by sigma 2 square. So I have a random variable which looks like this actually, that has a mean 0 and the variance is sigma square, where the sigma is this sigma 1 upon sigma 2. And let's compute what do you call the expectation of y. So if you compute the expectation of y, you're going to get again 0 because this is going to be expectation of x2 minus mu2. And if you compute, for example, the variance of y, you're going to get variance, so 1 over sigma 2 square times the variance of x2. But the variance of x2 is what? Is what? Is sigma 2. Sigma 2 square actually. So sigma 2 square divided by sigma 2 square is going to be 1. So y is a random variable that has a mean 0 and 1. Now I know, so here's an interesting thing. Now I know that x plus y is normally distributed. So x is like 0 sigma square and y 0 1. Then x plus y is going to have a normal distribution 0 plus 1 plus sigma square, where the sigma is sigma 1 over sigma 2 square. So it's going to be 0 and 1 plus sigma square, which is sigma 1 over sigma 2 square. Okay? So we know the distribution of these two guys. Now I would like to call you to recall a fact actually that we talked about. That if, for example, W is a, or maybe, I don't know, X is a random variable, maybe F is a random variable that is normally distributed with, say, mean mu and sigma square, okay, then AS plus B, in other words, that you multiply it with the constant and add the constant, is going to be normally distributed with mean A mu plus B and variance A square sigma square. In other words, this coefficient is square sigma square. Now, so you have like this x plus y multiplied by sigma 2, and you know about the x plus y, okay? So take this s to be x plus y, which is same as this. So this is like your s, and take this constant as a and this constant as b, okay? And then substitute the values here. So what you're gonna see, that eventually your x1 plus x2 would be normally distributed with the mean what? So your A is a sigma 2, but your mean is 0. So the A mu would be 0. And the B is mu1 plus mu2. So you're going to have what? Mu1 plus mu2, and the variance of it is going to be A square. And what is A? So A is sigma 2. Okay? A square is sigma 2 ka square times sigma 2 ka square, yes, sigma 2 ka square times sigma square. And what is sigma here? So the sigma here is, in this case, sigma for S, because the S has what you call the mean sigma square, but the role of sigma square is playing this actually. So you're going to say 1 plus sigma 1 square over sigma 2 square is going to be this. And hence, if you simplify, sigma 2 square multiplied by 1 is going to give you sigma 2 square. Sigma 2 square will be cancelled with sigma 2 square, and hence you're going to get mu1 plus mu2 sigma 1 square plus sigma 2 square. So this is going to be the case, and hence we proved with the claim that if x is normally distributed with mean mu1 and sigma square, and x2 is another normally distributed random variable with mean mu2 and sigma 2 square, then their sum is also going to be normally distributed with mean mu and variance, what do you call, sigma 2 square actually. Let's do one example based on it. Let's do one example based on it and then finish our discussion. I will leave some of the things for you to do for yourself actually, or maybe I can discuss some of the things in our next discussion, that where you have to do this sum of random variables for different cases actually, when x is Poisson, y is Poisson and independent, when x is binomial and y is binomial, both are independent, then what would be the distribution of x plus y. So for some of the calculation you have to do yourself. Okay, so this is another important key fact that you have to keep for life in your head actually, and you can even generalize it actually. You can even generalize it that, okay, if you have x1 that has a mean mu1 and sigma square, sigma 1 square, and x2 that has a mean mu2 and variance sigma 2 square, and x3 that has mean mu3 and variance sigma 3 square, and xn that has a mean mu n and variance sigma n square, and then you sum their and you sum them. Their sum is also going to be normally distributed with mean mu1 plus mu2 plus mu3 plus mu n up to mu n, and variance is sigma 1 square plus sigma 2 square plus sigma n square actually. So you can extend this result inductively and prove the more generic statement actually. So do give a read to the things that are given in the book actually, especially in the proposition 3.2. So the proposition 3.2 actually. Okay. Facts, facts, facts. You need to keep the facts in head. And this is an important fact, that the sum of two independent normal random variable or an independent normal random variable is again an independent normal random variable. This was not true in case of what do you call, when you were trying to do the uniform distribution. So So let's do one example based on it, and let's use this fact that sum of two normally distributed random variables are normally distributed. Okay? And try to calculate some probabilities. And then we will end the discussion. Here is